So, all right, in lecture number 8, I want to talk to you about a concept called symmetry. You've done quite a few of these problems by now, both in two-dimensional trusses and three-dimensional trusses. And you've probably noticed, unfortunately, solving these problems takes a long time. It's a rather tedious process. And the problems you've been doing in your homework and that we've demonstrated in lecture are actually rather simple problems. They're designed to teach you the theory and the concepts, but they're not the actual kind of problems that somebody would actually use finite element analysis for. In a real problem, instead of having 2 or 3 or 4 elements, you might have 100, 1,000, or even millions of elements, which is why we typically don't like to do these types of problems by hand. That's what we have computers for. In fact, that's literally the reason we invented computers, was to solve these types of problems. But even for computers, when you have finite element analysis problems with thousands or even millions of elements, it can become rather computationally expensive and take the computers a long time or many, many processors to solve these systems. So sometimes we can use this concept of symmetry to take a very complex problem and turn it into a simpler or a smaller problem. In some cases, a much smaller problem. So there's a lot of different types of symmetry, and symmetry kind of depends on the properties of the object that you're doing your finite element analysis on. So different types of symmetry include reflective or mirror symmetry. There's skew symmetry. There's also axial symmetry and cyclic symmetry. But in this class, we're just going to focus on the first type, reflective symmetry. So what is reflective symmetry? Reflective symmetry occurs when the object you're interested in has some either line or plane that we think of as an axis or a plane of symmetry, where everything on one side of the plane or axis of symmetry is a mirror image of what's happening on the other side of the line or plane of symmetry. So everything's the same on one side as the other. The size, the shape, position of loads, boundary conditions, all the same on one side of your axis of symmetry as the other. Let's look at an example to demonstrate how we can use the concept of reflective symmetry to simplify our problems. Let's take a look at a problem. Here's a simple truss. Here's a truss. It has 8 bar elements, one located here, here, here. There's one here. There's another one here, here, and here. There are 2 pin joints supporting my truss, one located here and one located here. There's a force along this line applied at this joint or node here, a force with a magnitude of P. All of the bar elements have the same cross-sectional area A, and they all have the same Young's modulus. And I think you'd agree that this problem demonstrates symmetry, right? There's a line of symmetry along this line here. Okay? So everything's a mirror image. There's the same boundary conditions, the 2 pin joints. There's a bar on this side for every bar on this side. And if I was going to take this problem and apply a finite element analysis to it, I'd probably start by discretizing. I'd discretize and number all 8 bar elements. And I'd also label my nodes. Node number 1, 2 is up here, 3 is down here, here's 4, and here's 5. So again, we have 8 elements and 5 nodes. Now let's take a look at another truss. Here's a truss that's very similar to this truss, but it's different in a few key ways. One, obviously, bar element number 7, bar element number 6, and element number 8 are missing. There's no need for a pin joint here at node number 5. There are, however, new joints. There are roller there are rollers here at node number 2, node number 4, and node number 3, and these constrict those nodes so they can only move up and down along what in the original problem was the axis of symmetry. Of course, these nodes in the original problem, since the problem is symmetrical, we know that these nodes aren't going to move away from the axis of symmetry. They have no reason to, because any force acting on them in one direction is acting on them in the other direction, normal to the axis of symmetry. So they will stay along the axis of symmetry. The force applied at node 4 in the original problem is still applied at node 4, but is now at 1/2 the strength. Also, the cross-sectional area of the elements number 4 and number 5 are now half the cross-sectional area as they were in the original problem. Now, with these changes in mind, I think you'll agree with me that if I solve for the displacements at node number 2, node number 4, and node number 3, and the external forces that will be acting on our truss structure applied at node number 1, that these would be the same displacements and the same external forces that would be solved for in the original problem. But in this problem, I only have 1, 2, 3, 4, 5 elements. And 1, 2, 3, 4 nodes. It's a much simpler problem. And so I've solved for the displacements at 2, 4, 3, and the external forces at 1. I know those will be the same for my original problem, and I don't need to solve for the external force at node 5 because I know it'll be the same, or the mirror image of the forces at node number 1. So in essence, I have now solved all of the information I need for my original problem, solving the much simpler problem using reflective symmetry. So if you can use reflective symmetry to simplify your analysis, you can go ahead and do so. You need to follow the 3 simple rules. The forces on the axis of symmetry must be divided by 2. Now again, this is only for the forces that are acting along the axis of symmetry. If you have another force applied at a different node, then that node is not on the axis of symmetry. Even if it's parallel to the axis of symmetry, you do not need to divide that force by 2. Only the forces that are acting along the axis of symmetry, you would divide those forces' strength by 2. In your new problem, nodes along the axis of symmetry need to be constrained so that they can only move along the axis of symmetry. A node in my original problem along the axis of symmetry has no reason why it would move away from the axis of symmetry. And finally, any elements that are along my axis of symmetry, their cross-sectional area needs to be divided by 2. All right, so this ends our only part of lecture number 8.